Okay, so let's talk a little bit about something called resonance structures. These are an extremely important part of organic chemistry, so it's important that we try and get a stronger grasp on them as quickly as we can. So let's start off with a little bit about what exactly resonance structures mean and what they're used for. And so to introduce it, let's talk about what if I was to try to come up with the Lewis structure for the nitrate ion, NO3 minus. Okay, if we follow all our normal rules, oxygen's got 6 valence electrons, there's 3 of them, so that's 18. Nitrogen's got 5, that's 23. Negative charge gives us 1 more, so that's 24. Nitrogen can form 4 bonds, so nitrogen becomes the central atom. So we've got a nitrogen with 3 oxygens around it. And remember, we're trying to fulfill the octet rule for all of our atoms, but we should remember that because there's a negative charge here, at least for one of our atoms, we won't be able to fulfill that, because that negative charge says at least one of the atoms is unhappy and doesn't have its required number of bonds. So if we follow our rules, we fill in single bonds between the inner and outer atoms. And then let's have a look at, for example, our our nitrogen. Okay. We have a situation where we want our nitrogen to have 8 electrons around it, and we can do that. We can do that either by adding an extra pair of electrons, or by putting a double bond here. So if I was to do something like this and put these electrons here, then that gives me my 8 electrons around nitrogen, but it also means I can't put any more bonds to the oxygen. Now you guys know that oxygen normally likes 2 bonds, and if it doesn't have 2 bonds, then that means I have to fill the oxygen's octet, each of the octets for the oxygen, with 3 lone pairs. Well, those are supposed to be lone pairs. Now, if you add up all the electrons that we've used here, it's 8, 16, 24. We've actually used 26 electrons here, which should tell you something's wrong. That can't be right. So let me just start over again. We have our nitrogen, we have our oxygen, we have another one, and then we go to here, here, and here. So if we can't fulfill the electrons, if we can't fulfill the octet around nitrogen with a lone pair, we have to put a double bond. So if I was to do something like this, and I fill in the rest of my electrons, then I get to a situation where this oxygen now has its octet, this oxygen now has its octet, and so does this oxygen. Now, count up the electrons now. That's 8, 16, 24. That's actually the right number of electrons. Notice that this nitrogen doesn't have its required number of bonds. It has 1 too many. And these oxygens don't have them either. So because of that, they have formal charges. And if you go through the formal charge calculation, you'll find out this oxygen is -1, this oxygen is -1, and that nitrogen is +1. The overall charge for the ion comes from minus, minus, and plus, so 2 minus and 1 plus gives you 1 minus. So this is the valid Lewis structure for the NO3 minus ion, or at least the most appropriate. But then that might raise a question. Why is it that I put the double bond here? Why couldn't I put it between the nitrogen and this oxygen, or the nitrogen and this oxygen? Well, it turns out there's actually no reason why I couldn't do that. So another valid Lewis structure for the NO3 minus ion would be something that looks like this, with that double bond elsewhere. And then there would be a third one with that double bond here. Okay. So if we fill in all our electrons, now as I'm doing this, one question you might be asking is, well, that looks a little odd. All those look the same to me. All those 3 structures look the same. And to a certain extent, you would be right. But the fact is, these are all slightly, they're all not exactly the same thing, and let's just talk about what they actually are. What these are all examples of things called resonance structures. And basically a resonance structure is a situation you have where you can draw out more than one valid Lewis structure for a particular molecule. And resonance structures are really used to illustrate why something is more stable than it would otherwise be. Usually to do with placement of lone pairs and charges and pi bonds. But here we have an example where we can put this double bond in 3 different places. Here, here, and here. And we can actually show that these 3 structures are all interconvertible from one to another. In other words, I can take this negative charge here and move it up here. And then I can take this negative charge, let's see, I can take this negative charge and move it over to here to give me this resonance structure. And when you're talking about resonance structures, that's really what you're talking about, moving electrons from one place to another. So let me move on and talk about something a little bit less complicated. Let's take the acetate ion. Alright, and the acetate ion looks like this. So acetate, really, another name for acetate is ethanoate, but what's important is that we have 2 carbons, a carbon double bond oxygen and a carbon oxygen single bond with a negative charge there. The fact is that this negatively charged ion, this anion, is more stable than it would be expected to be. And the simple reason for that is you can spread that negative charge around more places than you would, for example, in a case like this. If we have CH3O minus here, there is one single place where that oxygen, where that negative charge is located, and it's on the oxygen. Here we have a situation where I can take these electrons and funnel them around somewhere else. Now, in order to be able to do this and have resonance structures, you need a situation where you have at least a 3 carbon unit, carbon 1, 2, and 3, where in one part of that unit there is a double bond. So let's say between carbons 1 and 2 we have a double bond. And then on carbon 3 there needs to be some sort of charge. It doesn't matter what the atom is on 3, there just has to be some sort of charge there. So it could be a minus, it could actually also be a positive charge. The important thing is that using the fact that you have this charge here and this double bond here, you can actually move electrons from one place to another. In the case of this acetate ion, I can actually say I'm going to move some electrons from my oxygen by the use of a thing called curly arrows here. This indicates a movement of electrons. I push these electrons in and make a double bond here. Now if I don't move any more electrons out, that means I have what we called before a Texas carbon. I have 5 bonds to that carbon, which we've said before we can't have. So if I push these electrons in, I got to push some other electrons out, and that means either breaking one of these 2 bonds or breaking this bond. And you guys have seen before which of the 2 bonds, pi or sigma, is the weakest and easiest to break, and that's a pi bond. That's why for resonance structures we need to have a double bond, because it's that pi bond that will break more easily than anything else. So I funnel electrons in, and I need a place to funnel electrons out again. Now let's see if we can figure out what we get after we've moved these electrons, because being able to figure out products from resonance structures is extremely important. Bear in mind, resonance structures are only differed by the location of a pi bond and a pair of electrons. Everything else stays the same. So I have an oxygen up here, I have an oxygen here, and all that's going to be different in my product is where my pi bond is and where my other electrons have gone to. So notice on this oxygen I originally had 1, 2, 3 pairs of electrons, but I've taken one of them and funneled it into this ring to form a double bond. So I got to draw that double bond on here. Also notice that I broke this pi bond and shoved those electrons up onto oxygen. So over here, that pi bond is broken and I'm left with one sigma bond. Over here, I originally had 3 lone pairs, but I used one of them to go into this double bond. So how many do you think I would have left here? Well, if you'd said 2 lone pairs, you would be right. I have 2 left because I used 1. And if the electrons from this pi bond broke and went onto the oxygen, how many pi bonds do you think I would have on the oxygen here? Well, it would be the original 2 plus the pair that came from the pi bond. Alright. And because this oxygen now only has 1 bond, it gets a negative charge. So what I've done is allow to spread that negative charge across from 1 atom to across essentially 3 atoms, the oxygen, the carbon, and the oxygen. And anytime you can spread charge around a molecule, you stabilize it. Okay? An analogy is, let's say you are walking on some ice, and you walk on there in some stilettos, for example. You put an awful lot of pressure on one small part of that ice, as you will with a stiletto. You're more likely to melt it at that point, make some water form, and have yourself fall over. If you wear some flat shoes where a whole bunch of that shoe touches the ground all at once, the pressure at any one point is much less. So that pressure is spread over a bigger area of that shoe. Less of the ice melts, less chance of you falling over. So it's kind of the same thing here. The more you spread the charge out, the more stable the molecule is. Notice here in this guy, there aren't any double bonds located 1, 2, 3 relative to the charge. So we can't move that around. So what that means is this has more places to shove the electron density around than we do here. So this ends up being more stable. So anytime you can show resonance for a species, it's going to be more stable than for something you can't. Okay. Now here we started with a negative charge. Negative charge means we have lots of electrons to move around. What if we didn't have any electrons to move around on that initial carbon? Here we had electrons to move. When we have a plus charge, though, that just means that is essentially an empty orbital. There are no electrons to move. But we have to move electrons from somewhere, and we always start moving electrons from the site of highest electron density. In a species like this, it's where there's a negative charge. In a species like this, I'm hoping you guys would see the area of highest electron density is not the plus charge. It's actually the double bond, or the pi bond. And so that's where the electrons would start to move from. And the idea is to move some electrons here to do something to make that plus charge move somewhere else. In this case, these electrons will go over to the bond here. And once I reform that bond there, if these electrons in this pi bond have moved over here, then I now have a pi bond here. If that's the case, then there were originally 4 bonds on this carbon, because there are 2 hydrogens that we knew were there, we just didn't have shown. And if those 2 hydrogens are still here, we haven't moved any hydrogens, so how many bonds do I have on this carbon now? Well, the answer is 3. And if we figure out the formal charge there, that means we have a plus charge on that carbon. So we've moved our plus charge from one place to another. And that essentially is what resonance structures are all about, moving charge from one place to another. So let's see if we can go through a couple of examples here. If I was to draw out a structure like this, this is a 6-membered ring, and I'm going to I'll put a methyl group there, I'll put a plus charge here, and I'll put a double bond here. Remember what we said before about the 1, 2, 3 relationship. In order to have any hope of resonance capability, there needs to be this 1, 2, 3 relationship between the double bond and the charge. No matter what these atoms are, they could be oxygen, nitrogen, phosphorus, sulfur, it doesn't matter. What matters is there's a charge here and then a double bond here. Okay? And in case you're wondering why I'm linking my resonance structures with this arrow, this is a resonance arrow, a double-headed arrow, okay? Meaning we can go both ways, one way and the other. So, what would the arrow or arrows look like in terms of what would happen here? Well, let's just go back to what we saw here with the plus charge. Remember, the electrons move from the site of highest electron density to begin with, which in this case is our double bond. So the electrons would start to move from here. Either they're going to move around here, or they're going to move around to here. Now, they want to move around to counteract something that's missing electrons, which is the plus charge. Okay? These don't go directly onto the plus charge, because that would mean we're forming a new bond, and that isn't what's happening. We're just looking to find a way to give this carbon its fourth bond back and have one of these three carbons lose a bond, allowing us to move the plus charge elsewhere. So if I just move that over here, I could also show that arrow down inside the ring if I wanted to. Doesn't really matter. And I draw this out again, and I just label these three carbons again, 1, 2, and 3. Between which two carbons is that double bond going to be now? Well, it was originally between 2 and 3. The arrow shows it's now going to be between 1 and 2, and I'll just draw it there. But if that's the case, which out of carbons 1, 2, and 3 here lost a bond, and thus which one has the plus charge over here? Well, it can't be carbon 1, because carbon 1 actually gained a bond. Carbon 2 has 4 bonds here and 4 bonds here. Now carbon 3 is the only one that's different. It lost a bond. So there we've shown two resonance structures. And there's really nothing else we can draw, because there's only one situation where we have the 1, 2, 3 in terms of our charge and lone pairs. Let's do another one. What about if we had a 5-membered ring here? Except I'm going to say, rather than having a plus charge, we have a pair of electrons on this carbon. And because of that, we have a negative charge here. And let's say we also have a double bond here. In fact, let's say we have 2 double bonds. This is symmetrical down here, so we can go 1, 2, 3 this way, or we can go 1, 2, 3 this way. It actually doesn't matter which way we go. So I will choose for you guys. Let's say we go around to the right. Remember, the rule is we always start pushing arrows from the site of highest electron density, and when there's a charge, a negative charge, that's it. So these electrons are always going to move into the adjacent bond, which means into here. At that point, you've formed a double bond here, which means there's 5 bonds on this carbon, which you can't have. So the electrons in this pi bond are going to have to leave and go somewhere else. Now bear in mind, in a resonance structure, we originally had 2 pi bonds and a negative charge. The ideal situation is for us to reform another pi bond and reform the negative charge. So that means that charge has to end up on a carbon. So the electrons that we break here have to end up on a carbon. And they're going to end up either on this carbon or this carbon. Now the rule here is you want to make sure that your arrows, for the most part, follow the same direction. So here my arrows are going down, and this arrow is going to go down as well. So down onto this carbon. Also bear in mind that if we didn't do that and we went back up here, we would have here a carbon with 4 bonds and a negative charge, which is not possible. That carbon would have exceeded its octet. So if I draw this out again, can you guys see that this double bond actually hasn't changed? And if I just number all these, 1, 2, 3, 4, and 5, and then just number the began here, 1, 2, 3, 4, and 5. That's supposed to be a 3. The double bond that we originally drew was between carbons 2 and 3. Can you all see where that new double bond is now? Well, it's between carbons 1 and 2. Right there. The charge, the negative charge, was originally on carbon number 1. But where is it now? Well, you just follow the arrows, and wherever the arrows end up is where that negative charge is. It's here. But is that as far as we can go? Can we do anything else? Well, we just want to ask ourselves, do we have any more situations where we have the 1, 2, 3 relationship between double bond and charge? Well, 3, 4, 5 here is actually the same as saying 1, 2, 3, so yes, we can do that. These electrons can go into here, do exactly the same thing as they did before, and then go on to that carbon. And actually what we'll find out here is that we can keep on doing this until we've gone all the way around the ring. I'm not going to draw all these structures out, but if I just draw out this one, double bond goes here, double bond goes here, and we have a pair of electrons here and a negative charge. I'll tell you, there are 2 more resonance structures for this guy right here. So let's see if you guys can draw those out. So that, in essence, is resonance. These are resonance structures, and that's it. Thank you.